Hello, everyone. Welcome to the fifth seminar in the Clever Planets seminar series. So this seminar is going to be given by Renyu Hu from JPL. Before I introduce you to the speaker, I'll have a few words about the Clever Planets group and the land acknowledgement statement from Rice University. So the Clever Planets is a multi-institutional interdisciplinary initiative to unravel the conditions of planetary habitability in our solar system and beyond. Its lead institution is Rice University and is supported by NASA. It's one of the teams of the Nexus for Exoplanetary Science System Coordination Network under astrobiology. And this is the land acknowledgement statement. Our research at Rice University is pursued on the traditional territory of several native peoples, namely Karankawas and Sanas, as well as the Cohicutans, represented today by the Tapelam Cohicutan Nation, and the Aishaks, represented today by the Atakapaishak Nation. We see as a duty to acknowledge the historic aspect of our identity and to foster a beneficial environment for all communities, in particular those who preceded us on this land. Yes. It's my great pleasure to introduce today's speaker, Dr. Renyu Hu from JPL. So today's talk is going to be on characterizing atmospheric chemistry in temperate exoplanets. Dr. Hu completed his bachelor's at Tsinghua University, followed by a master's at École Centrale Paris, as well as at Tsinghua University. He did his PhD in planetary sciences, working with Sarah Seeger at MIT, and he followed by a postdoc as a Hubble Fellow at JPL, and now he's a research scientist at JPL. His fields of interest are broadly the atmospheric characterizations of Earth-sized to Jupiter-sized planets and exoplanets. The techniques he uses are remote sensing of planets using transit spectroscopy, phase curve mapping, and direct imaging. Before I give the stage to Dr. Hu, I just want to say that the questions can be the questions would be taken after the seminar. You can write the questions either in the Q&A box, or you can raise your hand at the end of the seminar, and I'll read out the I'll unmute you and you can ask the questions. So Dr. Hu, the stage is all yours.
Okay, great. Well, thank you for the kind introduction. Let me start to share my screen here. A second. Okay, so thank you very much for inviting me to give the seminar. It's a great pleasure to be here. So today I will discuss temperate exoplanets and their atmospheres. I think the observations of these very exciting objects are starting. So in today's talk, I will show you how understanding their atmospheric chemistry will be instrumental in guiding the observations and interpreting the results. So since the discovery in 1990s, exoplanets have been inspiring the exploration of the universe. Today, we already know planets of Earth size. We know planets that receive irradiation from their host, the star, as Earth receives from the sun. And we also know many planets that populate the parameter space that is not populated in the solar system. And very soon, our field will have the capability to ask and answer deeper questions about these planets. For example, what are their atmospheres made of, and do they have a liquid water ocean? So exoplanet discovered to date has already shown a great diversity in the range of plausible planet composition and climate. So in this chart, the equilibrium temperature is a measure of the planet's bolometric irradiation, which is a key input for the physical state of the volatiles on the planet. And the radius of the planet on the other axis can tell us approximately what the planets are made of. So the marker size in this chart are scaled according to the signal-to-noise ratio we could expect from a James Webb observation of the planet spectrum, assuming that it has a hydrogen-dominated atmosphere. And you can see that some planets are more observable than others, but many planets that occupy a particularly interesting parameter space, for example, this intermediate size regime that is shown by the pink color, or the low temperature regime like 200, 300K. So there are actually planets in those parameter regimes that are amenable for atmospheric characterization now and soon and in the near future. So notably in this intermediate radius regime, from rocky to gaseous planets, and in this chart is between about 1.7 to 2.5 Earth radius, a planet in this size range could have a hydrogen-helium envelope or a larger or a large water layer or both. So to understand this degeneracy and figure out what the planets in this radius range are made of, have driven the exoplanet studies in recent years. And in today's talk, I will show that this problem is also very important with regard to the type of planets on which we can search for habitable environments. And I think that this question will also underpin the exoplanet exploration in the era of JWST. So the distribution that the planets, the distribution of planets found by Kepler's mission's exoplanet search has provided some indication of what the planets in this, what I call sub-Neptune size range might be. So the planet search itself is complete or nearly complete for planets larger than Earth and having orbital periods less than 100 days. And the results is summarized in this plot on the upper left. So how to interpret this, this plot is one of the frontier of exoplanet study. So if we start from the assumption that the two peaks, indicating two populations, the two populations originate from a same parent population, and then the interpretation could be that the smaller radius peak were the planets that have lost most of their primordial gas envelope, and the larger radius peak were the planets that have retained most of it. And under this interpretation, the two apparent populations could indeed come from a same type of protoplanet, that is rocky cores plus nebula gas. And therefore, in this framework, the sub-Neptunes, this peak here, should be mostly rocky cores plus a massive hydrogen-helium envelopes. Now, this statistical interpretation is somewhat supported by the location of the gap, which is defined as the minimum here, with respect to the level of stellar irradiation. So on the lower right is the expansion of this plot, but on to another axis, that is the stellar light intensity relative to Earth. And we can see that the gap here seems to decrease with for less irradiated planet. And the basic idea is that if you have a higher irradiation, the larger the planet must be to keep the primordial envelope, and thus the gap should appear at a larger planetary radius. So this interpretation seems to a certain extent consistent with the data. But on the other hand, it is unclear whether the radius gap actually extends all the way to temperate planets, where the stellar light intensity on the planet is more or less Earth level. And we could still ask the question whether the photoevaporation or other form of Emerson escape was the main cause of the radius gap in the first place. So there are some reasons that may suggest that the super Earths, which I will use to refer to the first peak in the previous chart, the super Earths and sub-Neptunes are not two evolutionary outcomes of the same parent population, but rather two intrinsically different type of planets that were formed with different planet building blocks. So in this alternative view, some super-Earths are built, some Neptunes are built with water, which takes up about 50% of their mass. So the plot on the left-hand side shows the mass and the radius of the planets and compare them with the modeled mass radius of several assumed planet composition. And if we just focus on the group of planets in the middle of the plot, and that corresponds to the sub-Neptune population, and we see that the mass and the radius of the sub-Neptune population can be well explained by planets with about 50% of their mass in water. So that's why this kind of planet is usually called water worlds. So the water world is at least consistent with the mass and the radius of those planets. And a second reason or a second line of indication that was suggested by this plot is we can, in addition to looking at the radius distribution of the planet, we can also look at the mass distribution of the planet. And the sub-Neptune population, the mass distribution is shown here by the blue curve, and the super population, the mass distribution is by this red curve. So we see that the sub-Neptune is actually much more massive than super-Earths. So the sub-Neptune is about 8 to 10 Earth mass, whereas super-Earth is about 5 Earth mass. So this may be inconsistent with the atmospheric escape interpretation, because the hydrogen and helium envelope that was supposed to be responsible for the size of the sub-Neptunes at most can take about a few percent of the planet mass. So losing that envelope, while it will reduce the radius, it will not reduce the mass of the planet, at least not so significantly. But on the other hand, this difference could also be potentially explained as a selection effect, like the more massive planets tend to be better able to retain the envelope. So more study would likely to be required. And lastly, the planet formation models have also indicated that we could expect some diversity in the planet's building blocks. So the planet composition are determined, according to planet formation models, are determined by their position relative to different condensation fronts or ice lines throughout their growth. So as the water ice lines sweep across the polar planetary disk from for around sun-like star from about 5 to 1 AU, it delivers water to planets that form in this entire range. So as shown in this one example in this lower right, this entire distance range would have a high water ice fraction in the planet that form. So the model actually suggests that the relative speed and the direction of the planet migration and inward drift of the water ice line is a main factor that determines the planet's water content. So for the reasons mentioned above, it appears to me that it is reasonable to expect a subset of sub-Neptunes to be water worlds. And the observation of those planets would be necessary for us to find out what fractions of them are water worlds and what fractions of them would have massive hydrogen helium atmospheres. So when it comes to temperate planets, whether a sub-Neptune is rocky planets plus massive atmosphere or a water world is even more important. And this is because temperate sub-Neptunes that have massive hydrogen helium that have a massive hydrogen atmospheres, they will be too hot at the bottom of the atmosphere for liquid water. But on the other hand, if they have large water envelope but somehow small hydrogen atmospheres, the temperature at the bottom of that atmosphere can actually be compatible for liquid water, and they can thus host a liquid water ocean. So, so the question is, how can we tell the difference between a temperate hydrogen-rich atmosphere versus a temperate water world? And we'll address this question later in the talk. And another type of temperate planets that we will search for potential habitability is, of course, temperate and rocky planets. And in that group, the most observable ones are the planets in the TRAPPIST-1 system. The recently updated mass and radius constraints, I think, make it very unlikely for them to host a hydrogen or helium-dominated atmosphere. So rather, any habitable scenarios on these planets are more likely based on a nitrogen and CO2 dominated atmosphere. So, so that would be our assumption for today's talk. But I would like to also point out that most of the small planets shown here are around M-dwarf stars, which has a different spectral shape compared to the sun. So how would this different stellar type impact the atmosphere chemistry and their habitability? So I think that this question must also be addressed by atmosphere chemistry models. So in the following, I will focus on two types of temperate planets: rocky planets like TRAPPIST-1 and volatile-rich planets like K2-18b and LHS-1140b. And as we'll have a wealth of JWST observations of these objects in the coming years, it is a great time to think about what their atmospheres might look like. So here's the outline of today's talk. First, I would like to discuss the atmosphere chemistry in temperate and rocky planets around M-dwarf stars using TRAPPIST-1 system as an example. I will highlight an CO runaway state driven by the stellar spectra, which we recently found to be a common phenomenon on this type of planets. So TRAPPIST-1 is a late type M star that is only 12% in radius compared to the sun. It has 7 planets with predominantly rocky composition, and 3 or 4 of the planets receive appropriate amount of irradiation to support liquid water oceans if they have the right kind of atmospheres. And TRAPPIST-1 is important because given the small size of the star, the planet's signal with respect to the star is the largest in the sample of temperate and rocky planets, rocky exoplanets we know today. So one key issue to keep in mind is that the UV spectrum of TRAPPIST-1 features large FUV emission, mostly in Lyman alpha, but very low near UV emission. So in this plot, I'm using GJA76 as the proxy because it is the M star that has the measured UV spectrum and also has a very similar effective temperature as TRAPPIST-1. But you get the idea that this kind of planets would have nearly the same far UV radiation as the sun, but near UV radiation a few orders of magnitude lower than the sun. So when we think about the habitability on the TRAPPIST-1 planets, and this is, I think this is likely the scenario that we have in mind. It will be to construct a habitable scenario. It will likely to have a nitrogen and CO2 dominated atmosphere, and the amount of CO2 in the atmosphere, as we well know, is regulated by surface or seafloor weathering. So 3D climate model of TRAPPIST-1e has explored the ice fraction as a function of different CO2 abundance in the atmosphere. And the models have found that you need about 0.1 bar of CO2 in order to have most of the planet's surface to be in the liquid form. Now we can ask the questions what this stellar radiation will do to this CO2. So the far UV radiation would photodissociate CO2 into CO and oxygen. But the reverse reaction of that is very slow. And so that free oxygen atoms will tend to recombine with itself to form O2. So if nothing else happened, this will continue and produce a CO and O2 atmosphere. Now you will ask, there are also CO2 in Venus and Mars atmosphere, and why this is not happening in the solar system. And this is because in the solar system atmospheres, there is a catalytic cycle that help recombine CO and oxygen and stabilize the CO2 atmosphere. And then the catalytic cycle comes from the photodissociation of water, and that gives rise to the reactive radicals in the atmosphere, OH and HO2, and these radicals will help the recombination of CO and oxygen and help stabilize the CO2 atmosphere. So one thing that the OH and HO2 can also do is they can recombine with themselves and form the reservoir species, which is at the bottom here, is H2O2. Now, this reservoir species is long-lived and does not participate in this catalytic cycle. So it's sort of like remove the radicals from being available to catalyze the recombination. Now, in the solar system, the H2O2 is quickly photodissociated by near UV radiation. So the balance tend to move this way, so the radicals can always be produced. But as I mentioned before, around late type M stars, because the NUV radiation level is low, then most of the OH and HO2 species will be locked into this reservoir species H2O2 and not able to participate in the catalytic cycle. And therefore, it will move the balance towards CO and O2. So this effect has been identified in previous works, but here I will be showing that around late type M stars as TRAPPIST, especially when you need to have a high abundance of CO2 in the first place, the impact will be very significant. So this is why I call it a O2CO runaway. So in this plot, I'm showing the results of the photochemical model. As the abundance of O2, CO, and O3 as a function of the input CO2 abundance. And you can see that when we increase the CO2 abundance from 10 to the minus 2 bar to 10 to the minus 1 bar, and we see that the oxygen abundance in equilibrium actually increased by several orders of magnitude. And so is the CO abundance. So an O2 and CO rich atmosphere turn out to be the steady state for the partial pressure of CO2 larger than 0.1 bar. And if we recall, the habitable scenarios itself for TRAPPIST-1e actually requires the CO2 abundance to be 10 to the minus 1 bar or more. And that means that the habitable scenarios for TRAPPIST-1 will likely imply a massive O2 and CO in the atmosphere. So what about this thin line here? So in these cases, I include a hypothetical direct recombination of O2 and CO in the surface ocean, which does not happen on Earth, but if there is abundant O2 and CO and there is life in that surface ocean, that might happen. And if that happens, that can indeed limit the buildup of O2 and CO. So that you may call that this is an anti-biosignature. But I would like to emphasize that this O2 and CO rich atmosphere is not a result of water or hydrogen loss, because the redox is actually balanced in the system. It is just a photochemical effect. It is the balance got shifted from CO2 more towards CO and O2. And how is that compared to the previous results? It's actually quite consistent, but here I'm showing you that when you further increase the amount of CO2, the response will be even more extreme, and you can end up having a CO and CO2 rich atmosphere, or even CO and CO2 dominated atmosphere. So let's spend a few minutes and to think about how the results can actually be wrong, because we want this to we want to test whether this is just a theoretical construct or something really can happen in nature. So we think about the robustness of the results from the atmospheric chemistry and also from the geochemistry perspective. In terms of the atmospheric chemistry, the buildup of the O2 and CO can actually help the direct recombination of CO and oxygen, because it increases the ambient pressure of the atmosphere. So now this has included in the model, and it does limit the buildup of O2 in the very high pressure cases. Another idea that other researchers have put forward is this NOx catalytic cycle that also help to recombine CO and oxygen, and then be produced by lightning in the atmosphere. So I have included that in the model, and as it turns out, the NOx species, it also has their own reservoir species, which is HO2, NO2. So if you're familiar with the terrestrial Earth's atmosphere chemistry, this is also well known as a reservoir species, especially during the night. So what we found is that most of the NOx species is going to be locked up by this reservoir species called HO2, NO2, shown in the green line here. And you see that NO and NO2 does not actually have a high abundance in the middle atmosphere, but rather HO2, NO2 is the dominant nitrogen species. And if we delete that species from the photochemical model, the NO will actually have much higher abundance. And actually, in that case, the oxygen buildup will be completely prevented. But that will be incorrect, because we know that HO2, NO2 exist, and it should operate also in the atmospheres of TRAPPIST-1 planet. And in terms of atmosphere chemistry, we have also implement the new water cross sections, and that have some minimal impact on the extent of the runaway, but it does not prevent the onset of the runaway. So one can also think about this problem from the geochemistry perspective, to think about whether there will be a sink of oxygen and CO in the ocean. So we have implemented an alternative boundary condition that mimics the recombination of O2 and CO in hydrothermal circulations through mid-ocean ridges. At least using the terrestrial parameters, we do not see a noticeable difference in the result. And also, we have also implemented, the oxygen deposition to oxidize the ions, and similar to the parameter space indicated by the banded ion formation on Earth. And we see that it does decrease the partial pressure of oxygen by about 10% in the runaway cases. So it does not change the results qualitatively. So to this day, the only mechanism that will prevent the oxygen CO runaway from happening, I think, is the surface ocean direct recombination between the O2 and CO, which is so far unknown to happen on Earth. So a brief summary of this part. I think the implication of this modeling study is that a habitable environment on TRAPPIST-1 planets likely entails an oxygen CO atmosphere. And this mechanism, this runaway mechanism, also applied to other temperate and rocky planets that are found around mid and late type M dwarfs. And the implication is that O2, CO, and O3 should really be considered together with CO2 and water as the primary molecules in search for atmosphere signatures from temperate and rocky planets of TRAPPIST-1 and other M dwarf stars. Conceptually, this is different from saying that oxygen is not a biosignal, it's not biosignal signature gas, or it's a false positive. It's actually a stronger statement than that. It says that oxygen and CO can actually be one of the dominant gas in the atmosphere, and therefore it controls the atmospheric temperature pressure profiles and the emergent spectra. And one can even think about detecting the oxygen and CO in the high resolution spectroscopy. So the point is that they probably is going to be a equally common molecule as CO2 and water in those words. So I think the observational studies of temperate and rocky planets that have nitrogen and CO2 atmosphere and oxygen atmospheres may be within the JWST. And if we come together and dedicate a large amount of time in a handful of targets. On the other hand, I think temperate planets with hydrogen atmospheres will be much more easily observed. And I think that these planets with hydrogen atmospheres will likely be the first one observed. So in the rest of the talk, I would like to discuss atmosphere chemistry in temperate and hydrogen or water-rich planets using K2-18b as an example. K2-18b is a sub-Neptune-sized planet in the habitable zone of an M dwarf. And it is hitherto the only known exoplanet that has an equilibrium temperature allowing water to condense in the atmosphere, and also a measured transmission spectrum, the spectral features. So it's shown in the plot on the upper left here. So its transmission spectrum was obtained by Hubble at 1.1 to 1.7 microns. And the spectrum clearly indicates spectral modulation, and this indicates a hydrogen-dominated atmosphere already. The spectral modulation, if the spectral modulation is caused by water vapor in the atmosphere, the spectrum can be best explained with water absorbing above a cloud at about 10 to 100 millibar pressure level. Self-consistent atmosphere models, however, suggest that methane contributes to most of the spectral variations seen here. So, but both the retrievals and forward models indicates that the atmosphere should be hydrogen dominated, and therefore we can say at this point that K2-18b should have a hydrogen-dominated atmosphere, perhaps some helium, and it also has water and or methane in the atmosphere. So as I have discussed in the introduction, the sub-Neptune K2-18b can either have a massive hydrogen atmosphere or a small hydrogen atmosphere overlaying a massive water layer. These two types of interior structure can give the same planetary radius for the same mass. So just from the mass and the radius of the planets, we cannot tell apart the two scenarios. So now let's take one step further and think about the chemistry of carbon and nitrogen species. If the planet has a massive atmosphere, thermochemical equilibrium can be achieved in the deep atmosphere. And for temperate planets, as we'll show later, thermochemical equilibrium will make sure that carbon and nitrogen to be in their most hydrogenated forms, like methane and ammonia. And these molecules will get transported to the observable part of the atmosphere and then undergo photochemical reactions and be converted to N2HCN, C2H6, and so on. And these gases will be transported down into the deep atmosphere and then recycled to the most hydrogenated forms. In comparison, if the planet has a small atmosphere, thermochemical equilibrium cannot be achieved. As we'll show later, for K2-18b, and I think for other temperate sub-Neptunes, a small atmosphere would have a temperate surface that is consistent with the liquid water. And then CO2 is likely the dominant form of carbon on the water world, and its abundance should be controlled by how much carbon that the planet formed with, and the partitioning of that between the iron core, the mantle, the water layer, and eventually the ocean pH. And in the atmosphere, CO and methane can be produced photochemically, but any ammonia should be dissolved in the liquid water ocean and thus completely removed from the atmosphere. And therefore, as we can see, for temperate planets at least, these two scenarios, the massive hydrogen atmosphere versus smaller ones, can be distinguished by detecting the signature gases and their photochemical products in the observable part of the atmosphere. And this concept, I think, opens up the possibility of observationally studying the atmosphere chemistry and potential habitability on temperate sub-Neptunes. So in the following, I will show you several key steps of the models and the reasoning with some details. So if you're very interested in learning about atmosphere chemistry, this should be a lot of fun to you. And if you come from other fields, just keep in mind that the things I'm about to mention will eventually affect the abundance of gases in the observable part of the atmosphere, and thus relate to the question of how can we tell. So first, let's consider massive hydrogen atmosphere. So here I'm showing in the black line the modeled temperature pressure profiles of the massive atmospheres for different atmospheric metallicity, 1 times, 10 times, 100 times solar abundance. And in comparison, showing the equal abundance curve between nitrogen and ammonia and between CO and methane, assuming thermochemical equilibrium. So the points here are where we expect the thermochemical equilibrium to be achieved. And one may expect that the mixing ratio of gases at this point will be carried upward to the observable part of the atmosphere by vertical transport. So first of all, we can see that this temperature pressure curve are all like below those lines. So it means that the dominant carbon and nitrogen species are indeed methane and ammonia. And we can see that also in the with the supersolar metallicity and also with the internal heat, and therefore the temperature profiles go like this. At some point, this can get actually quite close to the equal abundance curve. And as you can see from these numbers, the abundance of CO and CO2 and the abundance of N2 can actually be quite substantial. And I would like to draw your attention particularly to this number here. Even though we have quite a substantial amount of CO and CO2, the amount of CO is still like an order of magnitude greater than CO2. And this only happens if we have internal heat that increase the temperature of the deep troposphere. So without the internal heat, the temperature pressure profiles will go straight down like this. And and this additional CO, CO2, and N2 would not be there. So we'll come back to see what will be the impact of these to the spectral features later on. So now the methane, ammonia, H2S produced in the deep atmosphere will be transported to the observable part of the atmosphere, and they are subject to photochemical processes above the water clouds. And we have used an atmosphere photochemical model to trace the reactions. And this chart shows you the results. So this chart shows you the mixing ratio of each of those gases as a function of the atmospheric pressure. I would like to draw your attention to the following two main features. So at the pressure level of about 1 Pascal, we'll have the photodissociation of methane and water. They occur approximately at the same pressure level. And as a result of the photodissociation of methane and water, we see the formation of CO, CO2, and a little bit of hydrocarbons. And the next feature, at the pressure level of about 10 Pascal, there is the photodissociation of ammonia. And that photodissociation of ammonia produce N2 and HCN. And the HCN feature, and the HCN can actually build up to a fairly substantial abundant mixing ratio in the atmosphere. So we'll go over these two features in the subsequent slides. So feature one, the photolysis of methane together with water. So the basic point that we found that to be quite surprising is that the photolysis of methane together with water does not lead to abundant hydrocarbons. And if you are somewhat familiar with the atmosphere chemistry of the giant planet in the solar system, the photolysis of methane in those atmospheres generally give rise to fairly substantial abundance of hydrocarbons. But if you move Jupiter to Earth's orbit, this is an analog of what we have done here, more water will make to the upper atmosphere, and then the photolysis of water together with methane can actually prevent the abundant hydrocarbons from being formed. And instead, the most abundant photochemical products becomes CO and CO2. And their formation mechanism is more or less captured by this, by the very complex network shown here. And then if we remove that water, for example, if we test out a very cold exoplanets with the temperature similar to Jupiter, and therefore water is completely condensed out and then removed from the upper atmosphere, then again, the C2H6 will become the dominant photochemical products. So the point here is on temperate planet with hydrogen atmosphere, because you have photolysis of both methane and water at approximately similar pressure range, this will strongly limit the production of hydrocarbons and favors the formation of CO and CO2. So the feature number two is the photolysis of ammonia in the presence of methane. So if you recall that NH3 photolysis is at a pressure level below the pressure below the CO2, below the methane photolysis. So basically, the NH3 photolysis would occur with the background presence of methane. So when that happened, I found that on temperate planets, HCN is consistently the most abundant photochemical gas. And the mechanism goes like this. So NH3 will get photo-dissociated into NH2. So one path for NH2 is to recombine to form N2H4 and then going through the cycle and then eventually become N2. But on the other hand, if there is CH3 around in the atmosphere, then NH2 can combine with CH3 to form CH5N, and then photodissociation, and then eventually become HCN. So the source of this CH3 obviously is the most important process that enabled this network. And in this work, we found that the most important source of CH3 is the hydrogen plus methane and goes to H2 plus CH3. And then this hydrogen actually comes from the photodissociation of NH3 itself. So this mechanism therefore does not require any high energy radiation. It only requires the photodissociation of ammonia in the presence of methane. So this happens quite uniformly in any temperate atmospheres that has hydrogen, that has ammonia and methane. And why it does not happen in Jupiter? We know that Jupiter's atmosphere does not have much HCN. And the reason is that it's too cold. This reaction here, hydrogen plus methane, has an activation energy pretty high, and it only occurs substantially with at a temperature higher than about 200 K. So in Jupiter's atmosphere, where the photodissociation of ammonia occurs, the temperature is actually much colder than that. So this network becomes very limited in colder planet, but it will be very efficient on temperate planets. So that's one of the points I would like to make, is that the HCN is quite naturally produced in temperate and hydrogen-rich atmospheres. So then in this chart, I show the impact of any deep tropospheric source or sink of gases. So if you recall, a hot deep troposphere will produce appreciable amount of CO and CO2 and N2 at the expense of methane and NH3. So the thick dashed lines here show what happens if they are incorporated in the photochemical model. And we see that when you include the deep troposphere source and sinks, the atmosphere will have much less NH3. It actually virtually disappears in the middle atmosphere. And accordingly, it will also have much less HCN. And then the atmosphere will have much higher mixing ratios of CO and CO2. But again, the mixing ratio of CO is about 10 times greater than that of CO2 in the observable part of the atmosphere. Now let's turn to the small hydrogen atmosphere or water world scenarios. So as a theoretical limit, one can imagine a planet without any carbon. But I think this is unlikely because planets should form with some carbon. So what is a more plausible lower bound for CO2 for a water world? So to that end, we have developed a cosmochemically and geologically reasonable lower bound. Edwin Kite from Chicago contributed a lot on this estimate. So the basic idea is that we consider the partitioning between the iron core and silicate mantle, as well as the partitioning between the water envelope and the silicates after the planet formation. And the basic point is that even though most of the carbon will be in the core, still significant reservoir of carbon would exist both in the silicate and in the water envelope. And then following the formation of liquid water ocean, almost all of the CO2 will be dissolved in the ocean. And a higher oceanic pH will lead to more effective dissolution and less CO2 in the atmosphere. So now starting from about 1% in mass of 1% carbon in mass in the iron and rocky building blocks of the planet, which I think is a reasonable lower bound. If we compare the lower bound for primordial carbon endowment, if we compare that to the carbon content in primitive chondrite meteorites. And also, if we work with, assume an ocean, a fairly basic ocean as a soda lake in California, we can obtain a lower limit of atmospheric CO2 that is approximately corresponding to about 400 ppm with respect to a 1 bar atmosphere. And so this is what we have assumed here as the reasonable lower bound in model 1. And we also consider an upper limit of about 10% of CO2, and that is the upper bound. So for both CO2 and members, we found that liquid water ocean with 1 bar hydrogen, and this may sound okay. I guess I'm almost done here, and then we can have some discussion. So so I guess I have already talked about the lower bound of the CO2. And then the upper bound, we just assume that's 10%, because above which the atmosphere will appear will just no longer appear to be hydrogen dominated. So for both CO2 and members, we found that the liquid water ocean can form with 1 bar hydrogen. And this may sound quite small and constrained, but for less irradiated planets, a larger atmosphere will still be compatible with a liquid water ocean. The figure on the right-hand side shows you the steady-state solutions of the photochemical model. And we found that the CO is produced from CO2 photochemically. But in this case, the CO versus CO2 ratio should be about 0.1. And then methane is also produced photochemically and can build up to a substantial mixing ratio. So finally, we can bring all of the model together, including the massive atmospheres at different metallicities and with deep tropospheric source and sinks, as well as small atmospheres with different amount of CO2. So all the massive atmosphere models and the small atmosphere models with low CO2 provide good fits to the Hubble data, but they differ quite substantially at longer wavelengths, at the wavelengths that will be covered by JWST observations. And that's where we can distinguish the scenarios. I'd like to draw your attention to 3 spectral regions, one A, B, and C. So in spectral region A, we see a feature of ammonia for the massive atmosphere models. But for small atmosphere models or massive atmosphere with hot deep troposphere, the ammonia will go away, and therefore we do not see the ammonia feature. And then in spectral region B, we see the substantial feature of ammonia and HCN. And again, for massive atmospheres with hot interior and a small atmosphere, we do not see ammonia or HCN, and therefore the transmission will be a trough here. And just by spectral region A and B, you can broadly tell the difference, but the massive atmosphere with hot deep interior and the small atmosphere will actually appear to be quite similar. So that's why we turn to spectral region C. Spectral region C would have spectral features of both CO2 and CO. So in the small atmosphere, the CO should be much less than CO2, and therefore you should see a big peak of CO2 and very little CO. But in the massive atmosphere with hot deep interior, that you will see that in terms of the abundance, the CO is actually more than CO2, and therefore you see a substantial peak of CO and less prominent peak of CO2. So at this point, we can summarize a roadmap to characterize temperate subneptunes. So starting from detecting a large features in transmission spectrum, and if we do detect the large features, that means it must have a hydrogen-dominated atmosphere. And then in the spectra, we can ask the question whether it has CO and CO2. And if it does not, then whether it has ammonia and HCN, and if it does, then it's probably a massive atmosphere with solar metallicity. And if it has CO and CO2, then we can then ask the question whether it also has ammonia and HCN. And if it does, then it's probably a massive atmosphere with high metallicity. And if it does not have ammonia and HCN, then we can ask the question whether the CO2 versus CO ratio is greater than 1. And if it does not, it's probably a massive atmosphere with high metallicity and internal heat. And if it does, then it's probably a small atmosphere likely to have a liquid water ocean. So I think that this is a method to observationally study habitability on exoplanets in the coming years. The main model uncertainty will be the temperature of the deep troposphere. As you can see that if you raise or decrease the temperature, it does changes the atmosphere abundance. And we will apply this method to K218b and LHS1140b with JWST observations. Those are the two most observable and confirmed planets to date. But we also expect another 5 to 10 planets as the follow-up and validation of TESS object of interest continues. Another 5 to 10 planets will become available, and we can study these temperate subneptunes as a group and find out, whether some of them are water worlds or some of them are having massive atmospheres and what the atmosphere metallicity will be. So in conclusion, temperate environments on rocky planets around late type M stars were likely to also entail a O2 and CO rich atmosphere. And temperate and hydrogen rich planets likely have detectable abundance of HCN produced by photochemical processes. And in those worlds, hydrocarbons are unlikely to have high abundance and to be detected. And in general, we think that transmission spectra with JWST can tell apart a small atmosphere versus a massive one on temperate subneptunes, and thus assess its potential habitability. So I will leave it here. Thank you for your attention. I apologize for the technical issues, but I'm happy to answer any questions.
Thank you, Dr. Hu, for this amazing talk. Yeah, you can, if you have any questions, you can write in the question and answer chat box, or you can raise your hands and I can unmute you. You can ask your questions. But so there are a couple of questions there in the question and answer section. So this one question by Neil: what are the biases in obtaining masses for subsets of the sub-Neptune and super Earth populations?
That's a great question. It's manifold. It comes down to the detectability of masses by radial velocities, and generally speaking, the more massive ones are more likely to be observed and around more stable stars or brighter stars. But none of this, I think, it's very obvious in explaining the different masses distribution between the super Earth and sub-Neptune population. But on the other hand, there could be biases on the theoretical front, like the atmosphere retention theories may naturally requires that in order to retain a massive atmosphere, the core of the planet has to be larger than has to be as large as about 10 Earth's mass.
So there's a question by Carl. For the TRAPPIST planets, do you feel that you can rule out trace amounts of methane that dominate the spectrum and that lead to the global haze seen in the case of Titan?
Could you repeat the question?
For the TRAPPIST planets, do you feel that you can rule out trace amounts of methane that dominate the spectrum and lead to the global haze seen in the case of Titan?
Yeah, I don't think we can rule out the amount of methane by saying that it's more likely to have an N2 CO2 dominate the atmosphere. I guess it's just to say that methane will be photochemically unstable in those words, and it will be photolyzed and then probably eventually turn into hazes and remove from the atmosphere. But as Carl point out, this should also happen in the atmosphere of Titan, and yet Titan maintains a fairly substantial amount of methane in the atmosphere. So I don't think we can ignore the possibility that some of these worlds would have substantial amount of methane.
So there's another question by Neil. To what extent could M-dwarf stars, says strong flares, drive these model atmospheres out of equilibrium?
Right. So this is one area that is quite actively studied. There's recent observations of quite massive flares produced by M stars. So yeah, I think it will change. It will change the atmosphere composition. For example, where in the case of temperate and hydrogen-rich atmospheres, where ammonia get photodissociated, if you suddenly have a high amount of irradiation, then that should push the pressure level of the ammonia photodissociation much deeper into the atmosphere to probably the cloud deck, and then after the flares, it will gradually come back. So this will be an interesting effect to be observed. Probably as the secondary observation.
Andre, go ahead and ask the question.
Renyu, thank you for the nice talk. So you actually partially answered my question. It was very similar to Neil's question. So, if I understand correctly, for the late M star, you assume they have less UV than early type M star due to this is the photospheric UV. But for the late M star, most of the UV actually comes from chromospheric activity. This is what we're talking about, flares. So, and it's true it's periodic, but they are very active. So they stay active for a large filling factor of their life. So, how would that change your interpretation for TRAPPIST one? If you increase the UV flux.
You mean if we increase the new UV flux?
Yes.
I thought okay.
Because there is a lot of chromospheric, so I think I'm not an expert in the field, but I think the NUV flux for late M is chromospheric, it's not photospheric. So it comes from the stellar activity.
I see. I mean, I was just using that measurements from GJ876. I don't think there has been a very clear measurements from TRAPPIST. It's probably because the flux in the near UV is still quite low. There is only a measurement in the Lyman alpha flux of that star. But to some extent, I think it will come down to what the actual spectral emissions of those stars. But on the theoretical front, I'm happy to get more educated, and perhaps you can tell me about like if during the flares, for example, perhaps the spectral shape would change, and in that period, if the NUV flux will be actually higher, and then they would definitely change the atmospheric chemistry. But I think that even during the flares, the FUV will still get more the multiplication factor of the shorter wavelengths will actually be greater than the longer wavelengths, so that the ratio will actually be more extreme. But maybe that's case by case.
Yeah, again, I'm not an expert here, but I can send you some reference if you like. Maybe you already know them.
Right.
And they are not necessarily for TRAPPIST-1, is in general for late M dwarf. I'm not aware of any specific measurement for TRAPPIST-1.
I'll just take the last couple of questions. So there's another question. How high does the internal flux need to be to affect the atmospheric chemistry? For example, what is the assumed internal flux in your slide number 23?
Yeah, so I guess we can just bound the problem by saying that the internal flux of 0. So then you have an isosomal deep interior, and then in that case, none of the CO, CO2, N2 source will be there. So it will entirely be methane and ammonia. And then I think that in slide 23, we assume the Neptune's internal flux, which I think it's about 60K approximately. And that's 4K to 18b, which is a sub-Neptune. I think that's somewhat reasonable. And that would lead to some methanes and ammonia get converted to CO, CO2, and N2 at the deep interior. If the atmosphere is also about 100 times solar metallicity. So it's a corner of parameter space, supersolar metallicity and internal heat flux. Well, you can imagine an even higher internal heat flux, somehow the planet forms with very, very high entropy, or somehow the planet in the earlier history it's very difficult to lose much of the heat, and then you can potentially come up with other consequences in terms of atmospheric chemistry, but we haven't explored that in great detail yet.
That's the last question. In your small H2 atmosphere, why does the increased CO2 not increase the temperature in the lower atmosphere?
Yeah, this is a great question. First of all, H2 itself is a very strong greenhouse gas. It has fairly universal absorption across the wavelength range. So it does not have much window for CO2 to make a big impact. And if you recall the figure, it actually the CO2-rich atmosphere has a higher upper atmosphere temperature, and therefore the surface temperature is actually a little higher, but not substantially higher. So I hope that answers your question.
Yeah. Let's thank Dr. Hu again for the seminar, and I hope to see you all in a couple of weeks.
Okay, great. Thank you.